Hello again, my dear students, and welcome to the continuing of this case study. And our main concern now is toward the load profile. If you remember, in the previous part, we have reached this simple load profile demonstrating a sucker bump with 50% of the working time in the upstroke and 50% in the working time with the downstroke. Let's now start a new case study with a new load profile. And let's, as I mentioned in the previous part, let's consider, for example, a realistic living room case study for some fundamental loads. So let's say that we have lighting loads of, let's say, 500 watt that can reach 200 watts for a low level lighting, or what we can call during sleeping lighting. Then let's say that we have also an AC or an air conditioning of 2 kilowatts, so 1000 watts. And for example, let's say that we have a normal socket power of 100 or 1000 watts, for example. And let's say that also we have some high power sockets which consume 1500 watt. Okay, let's say this is our loads, and we need to calculate the energy across a day, or what's called the daily load profile. So as we did in the previous part, let's consider here time in hours. And let's now do it here. 1, 2, and so on. So this 24 represents the midnight, and so on. Okay, and now these are the powers we have. So we have lighting, we have air conditioning, we have normal sockets, and we have high power sockets. And here, let's do the total. Okay, perfect. So let's say, for example, the air conditioning is working during sleeping, for example. So let's say that it's working from, let's say, 5 p.m. We have here from 5 p.m. we have this 2K. So starting from 5 p.m., which is 17. So we have here this air conditioning. So let me fix the cell here. So this will continue here. And similarly, we have here again this air conditioning load. Sorry. So this is the air conditioning load. And let's say that this is continue till 7 p.m. So during morning time, usually people are in work, so we don't have, here we have zeros. Okay, so for the lighting, let's say that lighting is mainly during after returning back from work at 4 p.m. we will start have lighting, some sort of lighting, which represent this. So let's say this equal this cell. And then this is continue, for example, till sleep at let's say 10 p.m. And then during sleeping, we will have the low level lighting, which is only 200 watts. So here we have this 200 watts. Which will continue here again, this 200 watts. Which again will continue till the morning. And then let's say that here we will still have the same 200 watts just for security or something like that. Okay, then we have the normal sockets. So let's say that the normal sockets are working with different efficiency, with different capacities. So the normal sockets are working with this maximum capacity, maybe during the midnight, the midday from 4 to 10, let's say. So from this here, let's say this here, this is the normal sockets now. Which will work with full capacity here. Then we have a very few working hours. Then for example, we have this equals something like this times, for example, 0.3. So 30% only of the normal sockets are going to work. For example, the refrigerators or this fundamental loads or whatever. So here you see this is 300. And similarly, you can make it here. So we can just copy this formula. And then we can, yes, we can put it here, I think. So it will end up with the same 300, which will be a continuing node. For example, I'm sorry, this is, so I made some mistakes. So this is, yes, this is, I do some shifts. So this is the lighting. So this is the lighting, I'm sorry. And this is the normal. And let's do this is the high power. I'm sorry, I did some mistakes here. High. So let's assume that high power are only working during breakfast and lunch, for example. So it's in the early morning here at 7 a.m. We have this high power consumption due to heating food or cooking food or something like that. Okay. So this, for example, from 7 and 6, for example, and also at 5 p.m., for example, we will have the same. So we can use the same formula again. And we can go directly, for example, at 5 p.m. Yes, and put it here. Otherwise, let's say we have 0 high power loads. And here are another zeros. And here another 0. So as you can see, this is a very simple description. Of course, this is a very inaccurate description to represent different loads in a living room. So here we have the total, which is the sum of all these stuff. Yes, and then we can include the bracket. So this is the sum. And let's do it like that. Perfectly. But please don't forget that this is the sum in watt. Usually we are working in kilowatt. So what you are going to simply do is to take this and divide over 1000. So you get something like that. And then you can grab others. Okay, perfectly. So this is an example of what we can call a description for a load. Now, if we pick this one versus this one, we can now plot a very simple schematic for here. Yes, this is typical, as you can see. This is what we can call a daily load profile. So this is where you have a maximum power consumption and where you have a minimum power consumption. This very important profile, again, with x-axis representing time in hours and y-axis representing watt or power in kilowatt, and the area under this curve represents the total energy consumed per day in kilowatt hours per day. Of course, here you can take some decisions. So, for example, whenever you are considering a PV system, for example, you have to consider that you have, in this case, for example, you have what we call night loads. So you have to have a solution for these night loads, either using grid, if it's a PV grid connected system, or maybe using backup source like a diesel, or you have an alternative storage or storage bank in terms of batteries that can supply the load at the night. Of course, we are going to do this in more details while we are going through the course and the different sizing process in our course. But this should be considered, of course. But what you see here, my dear students, is simply what we call a daily load profile. But this daily load profile actually is not sufficient whenever we consider a full PV sizing system, because this only represents 1 day out of 360 days of the year. So we have to have this not only for 1 day, but for the whole year. Herein, my dear students, we have to consider something very fundamental, or we have to consider a new or another type of load profiles. So this load profile, let me write it here. I think I can use here a format, maybe, or yeah, I just need to remember where I can make. Yes. Okay, so I just need to remember how can I make a title for this chart design. Yes, so yes, it's true. So here, add axis title. So this is primary horizontal. So this is time. in hours. Sorry, so this is time in hours. And let's do it similarly for the y-axis. This is power in kilowatt. So this is simply how it's work. So now we can have a different way of representing our loads, which we can call an annual load profile. An annual load profile represents the energy consumption per year. So the x-axis will consider the number of months from 1 to 12, while the y-axis will consider the energy consumed per month. So how we can do this? Of course, in details, you can make it in a very accurate manner. So you can estimate the energy or the power, the annual, the daily load profile. And then by using this area under the curve, you can calculate what we can call the total energy consumption per day. Then you can sum for 30 days of January to get the energy consumed per January and so on. But in a little bit high speed way, we can consider what's called an average consumption. So, for example, as here in this case, we are considering an air condition and all these stuff. So this is a case to represent. So this is, for example, representing a day in a summer. So to calculate the overall energy, what we can simply do is going here. This is the power in kilowatt column. So I will go here and then I will calculate the sum here. And the summing function will consider all this data. I'm sorry. Let me do it once more. I'm sorry. Yes, I think I did some big mistake. So here, I will stop here and then say the sum function. And then I will consider all this data. And again, I think I did a mistake again. Yes, so this is sum. And now we can calculate. Yes, now we are working right. So I think this is correct. And then we can close. Yes. So this number, my dear students, represents what? Represents the energy in kilowatt hour per day. This is the energy, 52.8 kilowatt hour per day. This is the energy consumed. So now I will consider another table here. Let me. So now this will be the months. And this will be energy consumed per day. And here, energy per month. So simply speaking, now this is the month starting from January. So now here, as you can see, so it's only 12 months. Sorry. So we can just clear this. Okay, and here we have the energy consumption. So let's say, for example, this data we demonstrated together represent, for example, June. So this 52.8 will be go to June here. 52.8. This is per day. So simply per month, we can consider that this equals this data times 30. It will end up with 1584 kilowatt. So here it's better to represent this in megawatt, not in kilowatt, just to make numbers easy. So I will consider the same here with 1,000th division. So just for clarification here, the unit is kilowatt hour per day. And here the unit is megawatt hour per month. Okay. So we can simply apply the same equation among the all months. And similarly here. Okay. So let's say that this 52.8 will remain during not only in June, let's say till say September, and also in March, sorry, in May. In this period, we have this load. So here, starting from October, let's say, for example, we will somehow not use the air conditioning in a very continuous manner. So what I'm going simply to do is I will going to subtract this or recalculate this load without the air conditioning. So I will assume that no longer using air conditioning in October. So this is, let's say, total in winter. So this is simply will be equals sum of, so this and this, those, no, this is the total, so this is one. Or we can make it in an easier manner. I think we can make it not sum, so we can say that this is equals to this one minus this one in a simpler manner. That's right. And then we can calculate it across the board. And again, here you can have another version in kilowatts by simply taking this number with division by thousands, and then you can calculate here. And similarly, my dear students, you can have this number. We don't need this. So now it's only 22.8 kilowatts per day in average. So let's say in October, 22.8, this, and this is also 22.8. Okay, and let's say in also in March and April, 22.8 and 22.8. So, and let's assume that in December, January and February, you are using more lighting than usual because, you know, in winter, the day is shorter and the night is a bit longer. So let's say that here we will do another version for our loads and during the winter with higher lighting efficiency. So I will say that it's the same like here, but with, for example, extra 300 watts, for example, for lighting. So this is total. So I will call this actually total in spring and fall. And here I will consider that this is total in winter. Again, this is just a very trivial example to demonstrate that idea. Please don't restrict our numbers just for the idea. So, for example, here during the during the night hours, we will have our energy or our power actually is the same as in the spring plus this extra 300 watts representing, for example, extra lighting load, which will extend somehow till 7 or maybe 8. And then we will have it's the same as the winter or the spring loads here during morning, let's say for this, and then starting from 4 o'clock again, we have an early sun set in the winter, so that we will return back to have an extra 300 watt for lighting or whatever. So this is typically what happened. And again, this is in kilowatts. So let me add just more rows to separate, or more columns to separate. So this is in kilowatts, which will be easily here, this number divides by 1000. So this will end to be something like that. And again, we can calculate the overall energy, which is rise a bit. Now it's 27.9 kilowatt hour per day. So simply we will substitute here with 27.9 and another 27.9, and here again 27.9. Okay, so now we have a complete annual energy load profile. So what I'm going to do now is simply I'm going to plot this months against this, this months, yes, against this energy consumption. Let's make a plot now. So I think, yes, this one. Okay, that's perfect. That's amazing. So this is a real demonstration for energy load profile. Here, number of months. So now where we can go here, yes, and we can add axis, the primary axis. So this is simply the month, and what you can see here. So this is add an axis title for the also this one, which will be simply the energy kilowatt hour per month in, oh sorry, it's not a kilowatt, I'm sorry. Yeah, so this is energy megawatt hour per month. So perfectly. So now you can see, my dear students, the difference here and there. So here, this represents what we can call an annual energy load profile, representing the energy consumed across the year with different number of months. Each point in this curve is energy per month. And the overall curve gives you the detailed description of what we consider as the variation in the energy consumption across the year. Alternatively, what we have somewhere here, I'm not sure where it is, so most likely I deleted or for some reason or whatever, I don't know. So this one here, yeah, we have it. Yeah, this is one. Yeah, we found it. What we have here, my dear students, is what's called an daily load profile, which represents the total energy, the total energy consumed per day. In the x-axis, you have the hours, and in the y-axis, you have the power in kilowatts. And the area under the curve represents the overall daily load or power consumption, as overall daily energy consumption in kilowatt hour per day. However, in the other plots, this one, yes, the overall area under the curve represents the annual energy consumption. So if I go to this, so let me zoom out for a bit and let me move this, for example, here. If I go here, yes, and I make a submission, for this data. So what you will get here, my dear students, is 13.176 is 13.176 megawatt hour per year. This is the overall energy consumed by this system per year. So when we will consider the energy or the sizing of the system, which number we are going to consider? Or in other words, are we going to size our system based on the worst case scenario occurs in the summer, or based on the best or the minimum power consumption occurs in the spring and the autumn, or an average or a little bit higher than the minimum which occurs on the on winter, or in some sort of average in between? This is actually a very challenging question to be answered, because this is depend on what we can call the critical level of the load. To what extent your load is critical? Is it a very critical load that need to be supplied all the time under any circumstances? Is it a PV connected, grid connected system? This is a very important question, because if it's a PV grid connected system and you have a stable grid, then simply you don't need to design considering the worst case scenario. Because simply speaking, whenever your PV shortage the load, the consumption or the difference will be supplied simply by the grid. So you don't need to supply all the time. However, if it's a PV standalone system without any diesel or any other source, and you don't need your load to be off anytime, then you have to consider what's called the worst case scenario model. So your decision is depending on the circumferences or the conditions of the load. If the load is critical or not. And herein we can have different types of loads. So for example, we have what's called a summer loads, like what you are seeing now. So most likely our residential loads in relatively high temperature countries like Egypt are as summer loads, because in summer we consume more energy than in winter, simply because in summer we're using air conditioning. On the other hand, if you consider lighting loads in streets, this is a very typical example for winter loads, because night hours in loads are greater than night hours in summer. So usually when you are going to use when you are going to define only a lighting load, this will consume more energy in winter rather than summer, because the night hours in winter is greater. Alternatively, when you go to irrigation, usually in Egypt, irrigation rates or frequency of irrigation in summer is greater than in winter. So irrigation roads related to pumping systems on all these stuff are relatively considered as a summer roads. Another example, if you consider normal sockets in an office building, this is what we can call a flat load or a uniform load. Normal sockets are usually used to supply, for example, computers and printers and all this stuff. And usually speaking, in an office building, you use this in both winter and summer. That's why usually this is what's called a flat load. So it will be some sort of a horizontal line. Again, if you return to our previous example, my dear students, which is this sucker load pump. This sucker load pump is relatively a constant flat load because simply this field is working in both winter and summer. So in both winter and summer, you have the same amount of energy consumption. That's why we call it a flat load or a uniform load. So loads can different in terms of the level of critical, to what extent this load is critical, and also it can differ from the terms of their seasonal consumption. Is it a seasonal load like air conditioning and lighting, or it's a flat load or a uniform load like the case on office buildings and all this? And accordingly, you can have different sizing profiles or different load profiles. So in these two parts, my dear students, we have understood together what is the definition of the word load profile, how we can have what we can say a daily load profile considering power versus time or power versus hour, and how we can have an annual load profile considering what we can say months versus energy consumption periods. And as you can see, each of these load profiles can have its benefits in terms or in order to size your system. So in the next part of this lecture, my dear students, we are going to make use of this load profile in order to make a very initial steps toward sizing our PV system. Thank you very much for your consideration and see you in the next part.